The remains of biotic life have been found in 4.1 billion year old rocks in Western Australia. According to researchers, if life arose relatively quickly on Earth, then it could be common anywhere in the universe. Now that we have seen that fossils have been found which date back to billions of years, we come to the most pressing question: how did life originate on Earth? Sorry everyone, we had a slight glitch, but I hope it will now be okay. So I'll continue now. We have seen that fossils have been found which date back to billions of years. Now we come to the most pressing question: how did life originate on Earth? We will now we briefly go through each of the theories that answer our major question. I know that might sound a bit boring, but please keep your patience through them. The first theory we have here is the theory of special creation. According to this theory, God created the earth with all of its biodiversity altogether around 4,000 years back. But there is no scientific basis of this theory because it cannot prove the role of evolution in the creation of the present diversity and the presence of fossils. Next, we come to our second theory, the theory of panspermia. As far as we know right now, ancient Greek philosophers believed that life came to Earth in the form of spores or microbes from other planets. Well, meteorites found in Moray, Orgnell, Murchison have reported to have contained organic matter. The Murchison meteorite even contained a number of levorotatory amino acids. In 2011, Huawei found remains of bacteria in meteorites from Alaska, Siberia, and Antarctica. But do you not find it difficult to believe that life came to Earth in that way? Because the interstellar space has major lethal radiations and the outer atmosphere is terribly hot. So, though this theory proves the presence of some forms of life in both outer space and beyond, it does not explain the origin of life on Earth. Then we come to the theory, which was the most famous one in the 18th century, the theory of spontaneous generation. Also called the theory of abiogenesis, it believes that under certain conditions, non living substances could give rise to living beings spontaneously. Anaximander propounded origin of life from fertile Nile mud warmed by sun rays. Aristotle theorized that plants arose directly from the soil, worms and snails from products of putrefaction. But experiments of scientists like Francesco Redi, Lazzaro Spallanzani, and Louis Pasteur disproved this theory. Redi proved that flies develop from eggs. Spallanzani proved that broth decayed only in the presence of open jars, and Pasteur proved that microorganisms come from the air contaminated broths. Now, we come to the theory of chemical evolution of life. This is by far the latest theory about the evolution of life, and right now we don't have a better theory than this. It was proposed by Haldane and Oparin and expounded, and it is expounded in Oparin's book, The Origin of Life on Earth. The hypothetical proposals are chemical evolution, inorganic to organic molecules, but first life being formed by the assembly and interaction of organic molecules. This is the most scientific theory about the origin of life, and several experiments have proved that it might be true. Now, we will study about the conditions on primitive Earth. Like most other planets, Earth cooled after its formation, and different elements emitted materials outside from inside over the surface. Volcanoes emitted gases like hydrogen, carbon, nitrogen, oxygen into the atmosphere. Due to a reducing atmosphere in the primitive stage, these elements combined to form water, nitrogen combined with hydrogen to form ammonia, and methane, likewise from carbon and hydrogen, etc. Free oxygen was absent at that time. It is proved from the presence of ferrous element in early rocks compared to the presence of ferric element in the later, more recent rocks. According to Oparin and Haldane, early organic molecules generated spontaneously. The surface temperature was around 60 degrees centigrade, and due to the lack of enzymes and free oxygen, a hot dilute soup or broth filled the oceans, which contained organic compounds like sugars, fatty acids, glycerol, amino acids, and pyrimidanes. This was reciprocated in Stanley Miller and Harold Urey's experiment in 1953, which we are going to study right now. They stimulated the conditions prevalent on Earth at the time of abiogenic evolution of organic substances. They had a spark chamber with electrodes, a boiling flask, and a condenser. Miller used a mixture of methane, ammonia, hydrogen, and water. The mixture was exposed to electric discharges, followed by condensation and then boiling for 18 continuous days. The products were extracted and identified through chromatography. Miller was able to identify 15 amino acids, organic acids, ribose sugar, and purines like adenine. Occurrence of similar compounds in the meteorites show us that similar processes are occurring elsewhere in the space too. Sidney W. Fox in 1957 synthesized polypeptides by heating a mixture of amino acids at 160 to 210 degrees centigrade for several hours. In 1964, he synthesized ATP, porphyrin, nucleotides, etc., non enzymatically using hydrogen cyanide and inorganic phosphate. Orgel succeeded in synthesizing small nucleic acids from nucleotides under similar oxygen free conditions. Now that we know how organic molecules were formed, the question which arises is how did these compounds come together to form modern cells? So let's learn more about it. The organic molecules concentrated at the seashores and the crevices submerged in rocks to form a sludge like protein. Proteins form colloidal hydrophilic complexes which got surrounded by envelopes of water molecules due to the presence of residual valency. These aggregates were called coacervates by Oparin in 1923. Now, we see that Fox's iteration of this in the lab, where he called these aggregate like structures microspheres in 1957. He used intense heat, as was prevalent in primitive Earth due to lack of a fully formed atmosphere and volcanic eruptions, as the driving mechanism in his model. A particular mixture of pure dry amino acids was heated at about 175 degrees centigrade for 6 hours. Intense heating was seized and then the product was stirred with hot water and the insoluble material was removed by filtration. When the aqueous solution cooled, a product precipitated in the form of microscopic globules which Fox called proteinoid microspheres. Analysis showed that they consisted of polymers of amino acids, although shorter than lengths usually found in proteins. Some of these globules resembled coccoid bacteria, and others bulged and appeared to be budding, similar to certain microorganisms. Microspheres and coacervates fused into protobionts or self-replicating metabolic capsules containing various compounds like proteins, nucleic acids, carbs, enclosed within a lipid molecule. They absorbed materials through their outer surface and underwent physical enlargement. Division was physical, but let's learn the reason behind it. Because they still did not have their own genetic material as it was not fully developed yet. The most primitive cell-like structures were called protocells or eobionts. As proteins got associated with the membrane covering, they developed into chromophores, which could capture solar energy to provide energy inside the membrane. It was in these conditions that the first genetic material, that is RNA, developed. Can you think of any reason why RNA developed first? It is because RNA went both as genetic material and as a catalyst. Later on, as DNA evolved, because RNA is not as stable as DNA is, cellular mechanisms shifted to more protein based functioning. Protocells were pre living systems which had the machinery to perform several reactions, grow, and divide. The earliest cells evolved around 3.9 to 4 billion years ago in the soupy sea when temperature decreased below 50 degrees centigrade. Due to the absence of oxygen in the atmosphere was still reducing. The first single-celled prokaryotes were formed when eobionts collected more organic matter, formed cytoplasm to become the first living beings. They have naked DNA, protein forming machinery, mode of liberation of energy, its storage, and its utilization. They obtained organic substances from the environment and used it as fuel. They were chemoheterotrophs. But when the temperature dropped, abiogenesis stopped. Can you imagine what these would have done to those chemoheterotrophs? It led to a scarcity of food. They then evolved into chemoautotrophs, which could obtain energy from different inorganic matter. Such bacteria are still alive, like the sulfur reducing bacteria, nitrifying bacteria, and many more. Slowly, with the development of chlorophyll, came the first photovoltaics. And slowly, even more slowly, the reducing atmosphere changed into the oxidizing atmosphere we have today, which contains about 20% of free oxygen. Unicellular eukaryotes developed in these oceans about 1.5 billion years ago. As nucleus and other cell organelles developed, the cell became more active. In a major endosymbiotic event, eukaryotes engulfed purple sulfur bacteria, which are currently known as mitochondria. Can you imagine how chloroplasts came to be? It's a similar process. The invagination of the plasma membrane created endoplasmic reticulum and nuclear membranes. In a second major endosymbiotic event, some eukaryotes engulfed chlorophyll containing bacteria and gave life to primitive microscopic free living plants. Now, if anyone has any questions in the section we learned till now, can you please let me know in the chat? Okay, so I'm assuming that nobody has any doubts. Now we go to our next segment where we question ourselves, are we truly alone in this universe? Initially, scientists had assumed life is possible on planets similar to Earth, but now, from the data we have on exoplanets, which are planets orbiting a star out of our solar system, we have found that there are planets which exist, which are sub Neptune planets orbiting around M dwarf stars, which are far more suitable for life. So, we know for life we need few major factors, which is the presence of an atmosphere and the presence of water. That is what we have learned till now. That in our younger classes that we need oxygen and water to survive. But these sub-Neptune giant planets have hydrogen-dominated atmosphere. So now we need to see, can living beings survive in hydrogen-dominated atmospheres? Well, hydrogen is basically harmless to terrestrial life, but an atmosphere composed entirely of hydrogen would be fatal due to the lack of oxygen. It has been artificially simulated that organisms which do not live in hydrogen dominated atmospheres can live in 100% hydrogen atmosphere, which is entirely oxygen free. In this experiment, E. coli and S. cerevisiae, both facultative anaerobes, were tested. They grew at slower rates as compared to air. For yeast, that is Saccharomyces cerevisiae, the growth rate is much lower due to oxygen being a crucial substrate in the biosynthesis of many essential biochemicals. Methanogens and acetogens often are grown in an atmosphere of 80% hydrogen and 20% carbon dioxide. Also, hydrogen plays a very crucial central role as a reductant in many other anoxic organisms. Now, we come to our second atmospheric conditions, which is far more interesting than this. Some exoplanets even have carbon monoxide dominated atmosphere. We know that carbon monoxide is fatal for mammals, but it has no effect on multiple microbes which can live in just 100% of carbon monoxide. Sorry. Strains like Thermoanaerobacter, Thermohydrosulfuricus, and Thermoanaerobacter cuvoi can live in 100% carbon monoxide and use it as a sole source of carbon and energy. We can logically argue that any life in high concentration of carbon monoxide atmospheres would successfully adapt and possibly even exploit carbon monoxide for its own benefit. So, just because humans or mammals cannot survive in carbon monoxide dominated atmosphere, it would be a bit foolish for us to think that life might not be present there. Also, we know that carbon monoxide does not bind to all hydrogen oxygen carriers efficiently, and not all animals use hemoglobin as an oxygen carrier. Other carriers like hemocyanin, hemoerythrin, erythrochlorin, and chlorochlorine have much less carbon monoxide affinity than oxygen. It has been studied that hemerythrin from peanut worms has negligible binding to carbon monoxide. The available data right now supports the highly variable and species dependent effect on carbon monoxide on animal physiology. For example, deep sea toadfish survive indefinitely in 60% carbon monoxide. Freshwater goldfish survive exposure to about 80% carbon monoxide for two minimum of 2 days at 5 degrees centigrade. Xenopus levis frogs can withstand a near complete elimination of their hemoglobin due to carbon monoxide poisoning and recover without ill effects. Common fruit fly can be exposed to 95% carbon monoxide for up to 6 years. 6 hours without detrimental effects. Hence, the effect of carbon monoxide on animal physiology varies, and acute toxicity of carbon monoxide gas to mammals cannot be generalized across all animals, not to mention across all complex life. We know that on Earth, water is the basis of life. We even equate water to life. But does life really need water to be a basis for its foundation? No. Scientists are considering other solvents to be of the same in case of exoplanets. The prime candidates we have right now are nitrogen containing ammonia, which is pure ammonia in this case. Otherwise, it would be like an alkaline medium, and concentrated hydrogen sulfuric acid. As a solvent, liquid ammonia is almost as good a solvent as water is due to its high dipole and hydrogen binding network. It is a good solvent for a large range of solutes, even inorganic salts, and has a similar reactivity to water. Ammonia is stable unless it is disturbed thermally or photochemically. Even compounds like diazomethane and acetomethane, which are unstable on Earth, are stable in ammonia due to its much lower temperature. Hence, in an exoplanet having liquid ammonia as a solvent instead of water, it is highly probable that life will be present. Now, we will go to a very unorthodox solvent. The hydrogen, sorry, interest in sulfuric acid as a solvent for life was simulated by the possibility of life in the clouds of Venus. Recent modeling and studies have shown that sulfuric acid can stably dissolve a wide range of substances like DNA bases, amino acids, etc. In concentrated sulfuric acid, these diverse surfactants can form micelles and even liposome like structures. There are polymers which are soluble and insoluble in sulfuric acid. Also, several metal ions are soluble in sulfuric acid. But due to the high reactivity of sulfuric acid, many components of terrestrial biochemistry would be rapidly and completely destroyed in pure sulfuric acid. Can you name some of them? Well, they would be biomolecules having sugar moieties, like NADH, ATP, and RNA. So, sulfuric acid based biochemistry would be completely different from hydrogen monoxide based biochemistry, which is water based biochemistry. If an environment contains a range of sulfuric acid, concentrated one, organisms either use biochemistry that is appropriately stable in all concentrations or adopt a dormant protective form in lower concentration of the acid, which only maintains the active metabolism in concentrated acid, which is above 95% concentrate. So there goes my part. If anybody has any doubts regarding everything we have learned so far, please let me know in the chat. Otherwise, I'll delegate to the next lecture of the session.
Hello everyone, I am Abhishek from the Department of Metallurgical Materials Science in IIT Madras, and I'm here to talk about the topic Search for Life. Now that Ajiraj has explained how life evolves and how it can be in different planets, we are going to ask the question, how do we even search for life? What do we even have to search for life? Do we go to different planets and explore? how is that even possible? So the only clue that we have is light. So let us put on our detective hats and analyze this clue that we have as thoroughly as possible to draw our conclusions about the possibility of life existing in several other planets. To find life outside solar system, first we need to find planets outside the solar system. These planets that are outside the solar system are called exoplanets. Today we will see two methods to detect exoplanets. The first method is called the transit method. Imagine this. A star has a planet that is revolving around it, and the planet passes before the star, blocking out a tiny fraction of brightness of the star. This, while tiny, is still measurable by the instruments that we as humans have built, and thus, using the dip in brightness that happens periodically, we can verify whether or not a star has a planet that is revolving around it. So, this method is called the transit method. The next method that we have is called the radial velocity method. In order to understand this method, first we should understand the Doppler effect. You all would know the Doppler effect of sound, in which an object that is emitting sound waves, when it is coming towards us, each of the wave crest of the sound wave is spaced closer, leading us to perceive it as an higher pitch. Similarly, when the object is moving further away from us, each of the wave crest is spaced further away from us as time passes, leading us to perceive it as a lower pitch. Similar thing happens when Similar thing happens when an object emitting light is moving. The object, when it's moving towards us, we perceive it as a shorter wavelength and hence it is called as blue shifted. And when the object is moving further away from us, we perceive it as a longer wavelength and hence red shifted. Now to radial velocity method. When a star and planet pull each other, they revolve around their common center of mass, meaning the star itself wobbles around a bit as the planet revolves around us. And this wobble can be found out by measuring the radial velocity of the star, which can be found out by the Doppler shift. So we get the spectrum of the star, which is simply the light emitted by the star in different wavelengths, and see how much it is shifted, blue or in the red side, and find out the velocity of the star. So this can be used to verify whether or not a planet is revolving around a star. So is a planet so where is a planet existing alone is enough? No, we need to find out several properties of the planet like the radius and its mass. So first of all, the radius. So when a planet passes before a star, we, when a planet passes before a star, we observe a certain we observe a drop in brightness. So this drop in brightness can be measured to be F, and F is equal to radius of the planet divided by the radius of star squared. So why exactly? So this is because the amount of light that is given out by the star and the amount of light that is blocked by the planet is both directly proportional to the cross-sectional area of the star and the planet, which is directly proportional to the radius squared. So we get the radius of the planet. Any doubts that you guys have now, can you can ask. So, assuming that you guys don't have any doubts, the curious ones amongst you might have thought, like, to find the radius of the planet using this method, don't we need the radius of the star? And it is a really good doubt. So, basically, we can find the radius of star using multiple other methods, such as measuring the luminosity of the star, measuring the angular diameter of the star, and so on, which is outside the scope of this particular lectures. But I highly encourage you all to go and look up on this topic on your own. So, next, we need to find out the mass of the planet. Once again, the assumption here is that we already know the mass and the radius of the star, which we have found out in other ways. So we are going to find out the mass of the planet by radial velocity method. So using the radial velocity of the star, we get the shift in its spectrum, using which we get the velocity of the star. So basically, velocity of the star is equal to the speed of light into the change in wavelength divided by the original wavelength if the star were not moving. So using this Doppler effect formula, we get the velocity of the star. Since the planet and the star rotate around their common center of mass, they have the same orbital period and hence the same momentum. So basically, mass of the star into velocity of the star is equal to mass of the planet into the velocity of the planet. In this equation, we know the mass of the star and the velocity of the star, and we don't know the mass of the planet and the velocity of the planet. We are trying to find out the mass of the planet. So once we find out the velocity of the planet, we can plug it into this equation and very easily get the mass of the planet. So let us now concentrate on doing that. So there is one way to find the velocity of the planet, and it requires a couple of prerequisites. The eccentricity of the orbit. So basically, if the planet and the star both revolve around each other in perfectly circular orbit, the velocity versus time graph of the star will be perfectly sinusoidal. And how much it varies from being sinusoidal will be directly proportional to the eccentricity of the orbit. So the eccentricity of the orbit can be very easily found out using uh, observation of the radial velocity. So another prerequisite that we need is the time period of the orbit, which is very trivial. This is basically the time between two transits. Let me explain. So basically, a transit is observed when a planet passes right before the star. And when the next transit will be observed is when the planet revolves one complete revolution and comes back right before the star. So basically, the time period of the orbit is hence the time between two transits and can easily be observed. So now that we know all the data that we need by observation, let us run through the math and get the formula to find the mass of the planet. We have the time period, and we all know that Kepler's third law, which states that the time period of the orbit squared is directly proportional to semi-major axis of the ellipse of the orbit cubed. So basically, t square is directly proportional to a cube. So we know the time period, and we can very easily get the semi-major axis of the ellipse, which is the orbit. Now that we have the eccentricity of the elliptical orbit and its semi-major axis, we can find the circumference or the perimeter of the ellipse, which is the orbit. So now that we know the perimeter of the ellipse, which is the distance covered by the planet in one complete revolution, we know the time period, which is the time required for the planet to complete one complete revolution. So basically, the speed we get is distance divided by time, and we have got our velocity, and hence we got the mass of the planet as well. So now let us show the formula that we derived using all the steps that we saw in the previous couple of slides. So the formula looks a bit intimidating, but every single term here has been derived by us before. So k is basically the maximum velocity of the star that we are observing. P is the time period of orbit of the planet around the star. MP is mass of the planet. M star is mass of the star. And G is just a universal gravitational constant. And E is the eccentricity of the orbit. So you might be wondering what this sign I represents. So there is a small subtlety that I have not talked to you about till now, which I'm going to tell now. So basically, when we are observing the wobble of the planet in the radial direction, we cannot be sure that we are seeing the full wobble, because the full wobble might not be in the radial direction. A component of the wobble might be in a direction that is tangential with respect to us, which we cannot observe by the Doppler effect. So the sin I is basically what is the inclination of the orbit with respect to us. So we always assume that the sin I is basically 1, that we are observing the full wobble in the radial direction, but it need not be the case. So what we get in this formula is basically the minimum mass of the planet. We are finding a minimum bound to the mass of the planet. Where the planet might be much more massive because we are not seeing the full wobble that the planet causes on the star. So this is a subtlety that I want you guys to appreciate. So now that we know that a planet exists, its radius and mass, so what next? And also, why did we even find the radius and the mass in the first place? So let us approach this question, the second question first before going. So why did we even want to know the radius and mass of the planet? Knowing the radius and mass of the planet gives us the density of the planet, which helps us know whether a planet is rocky, like Earth, or whether it's a gas giant, like Jupiter or Neptune, which is a very important information to have about a planet. So now that we know that, how do we even search for life? So let us assume that we are an alien civilization and we are looking at a blue planet called Earth. What will we observe? We will observe an abnormal amount of oxygen in this planet's atmosphere, which is a very vital clue, which is a very significant clue in telling that this planet called Earth might have life on it. So similarly, us, when we are searching for another planet, we search for certain traces and certain marks which life leaves. These marks are called biosignatures. Some examples of biosignatures are oxygen, as I said, methane, nitrous oxide, and so on. So I would like to iterate on the fact that these are not definite proofs of life existing. They are subtle hints and indication of the possibility that life exists. So that we can observe more and form theories about the life that might exist on an exoplanet. So now that know that we are looking for these biosignatures, how do we find out these biosignatures? This is where we use the greatest toolkit in our toolbox, which is spectroscopy, where we use the light as our fingerprint to find out what are the composition in a exoplanet. So what are spectrum and how are they obtained? So basically spectrum is when we observe how much light is emitted by an object in a certain wavelength. So basically we collect light in an instrument like a telescope. That light is passed through an instrument like diffraction grating, which splits it up in several wavelengths. So we observe the light by capturing it in a detector and then we analyze it. So there are several types of spectrum that we can obtain. Let us go through a few of them. First is called transmission spectroscopy. When a star is emitting light and a planet passes right before the star, the light hits the planet's atmosphere and the planet's atmosphere will absorb certain wavelengths of the starlight. So once the light reaches Earth, we can see what wavelengths were absorbed by the planet and we can use that to infer what were the compounds that were present in the exoplanet's atmosphere. So for example, this is an sample of an exoplanet that is an Earth-like exoplanet. So here we can see that an absorption in these particular wavelengths denote the presence of molecular oxygen. An absorption in these particular wavelengths, here before like 8 micron and here before 2 micron, is denoting the presence of water. And an absorption in these wavelengths denote the presence of methane. An absorption in these wavelengths denote the presence of carbon dioxide and so on. So this is a very useful tool. This is like a fingerprint of the planet's atmosphere and every single molecule has its own unique fingerprint. Like water always absorbs in this region, carbon dioxide always absorbs in this region. So it's like matching fingerprints with what we already know by with existing templates of already existing molecules, and we can infer that these are the molecules that are existing in the exoplanet's atmosphere. A second type of spectrum is called the eclipse spectrum. In this, first we get the spectrum when the star and the planet are together, and then when the planet goes behind the star, in which we get an eclipse, we get the spectrum of the star alone. And once we subtract these both, we get the spectrum of the light that the planet emitted. The keyword here is the word emitted. The key difference between the transmission spectrum and the emission spectrum is that in the transmission spectrum, we get the spectrum of the light that the planet's atmosphere absorbs. But here we get the spectrum of the light that the planet itself emitted. So these are like two different sides of coin. When we analyze this, both gives us a even more deepened understanding of what exists in the planet's atmosphere. So this is an exoplanet VHS 1256b's emission spectrum. This was obtained by the near infrared spectroscopy instrument that was in the James Webb telescope. So basically, you can see the amount of light that was emitted by the planet in different wavelengths. So once again, you can see what the wavelength if planet emits wavelength in this region, it's water. A planet emits wavelength in this region, it can be silicates. In this wavelength, it is called methane, and so on. So once again, these are like fingerprints that we can use to match with our existing knowledge to find out what were the compounds that were in the exoplanet. A third tool that we have, which is not a spectrum but still a very powerful tool, is called as a phase curve. A phase curve measures the amount of light from the star plus planet system that we are observing that reaches the Earth during one complete revolution of the exoplanet around its home star. So here we can see that the exoplanet takes one complete revolution, and this is the amount of star that reaches Earth in this one complete revolution. Here we can see a big dip. This is because the exoplanet passed right before its star, blocking starlight and causing this huge dip. These two regions we see a minor dip. This is because the exoplanet went behind the star, meaning that the light emitted by the planet itself got blocked. This is obviously much less than this because light emitted by the planet is going to be much less than the light emitted by the star. So you might ask, how exactly is this useful? Let me give one simple example of how this is used. So basically, this dip has to happen when the planet goes right behind the star, right? That's what logic tells us. But sometimes what happens is that this happens just little bit to the east or little bit to the west here. So this is because of the planet has a wind system that scatters the starlight in such a way that you get this dip this side or this side, and not exactly when the planet goes behind the star. So this helps us to infer the wind cycles of the planet, to infer about the day night cycles of the planet, and so on. This is a very interesting field, and I encourage you all to research more upon it and study more upon it because it is very interesting. So now that we know these different types of spectrum and phase curve, the obvious question that we get next is how do we get this? What are the instruments that we use to get this? And the answer is telescopes and satellites that we have built. So the first telescope that we all would definitely have heard is the James Webb telescope. This was launched very recently by NASA, and it has several scientific instruments to get these spectra. So one of the scientific instruments is the NIRSpec, which is the near infrared spectroscope. It gets the spectrum in the wavelength region of 0.6 to 5.3 micrometer. These are very high quality spectra of exoplanet atmosphere and of galaxies. Next we have the NIRISS, which is the near infrared imager and slitless spectrograph, which gets a spectrum in 0.8 to 5 micrometer. This is designed specifically and exclusively for the exoplanet spectroscopy. Next there is MIRI, which is the mid-infrared spectrograph, which gets it in a much more higher wavelength than compared to these two, from 5 to 28 micrometers. In this wavelength, this is a thermal emission, so we get the spectrum of a relatively cooler object like brown dwarfs, exoplanet disks, and exoplanet atmospheres. The next instrument that I'm going to talk about is the Transiting Exoplanet Survey Satellites, or TESS. This is a space telescope launched by NASA in the year 2018. Its main job is to find exoplanets by watching thousands of the brightest and nearest star to Earth. And it uses the transit method to find out the dips in brightness of the planet when it passes front of the star. So TESS has 4 wild field camera, and they together cover the massive portion of the night sky. Each camera has a 24-degree cross 24-degree field of view, and TESS how it functions is that it divides the night sky into several sectors. So it observes each sector for 27 days before moving on to the next. So in this way, it efficiently maps the night sky and sees each part of the night sky for a much longer period and efficiently maps out each planet. Then there was the Spitzer Space Telescope, which was a NASA's infrared space telescope, which was launched in the year 2003 and was retired in the year 2020. Spitzer was one of the first telescopes to observe transits and the eclipses of exoplanets in the infrared region of the spectrum. It helps us to determine day-night temperature differences by using phase curves. So it also measured transit methods by measuring small change in brightnesses, and it also measured eclipses to get the emission spectrum. So then there is the Very Large Telescope. So contrary to all the previous instrumentation that we discussed, this is an on-ground telescope. So it is in Earth instead of being in space. It is a telescope facilities that is operated by the European Space Society, and it is located in Cerro Paranal in the Atacama Desert of northern Chile. The main reason this region was selected for building this telescope is that it is a prime site for clear and dry skies. Why do we need clear and dry skies? Obviously, because we do not want our Earth's atmosphere itself to interfere with the light that we are getting, so that we get the light from exoplanets and stars in a much clearer fashion. So what was very large telescope used for? It was used for direct imaging of exoplanets, which is a very interesting way to find exoplanets. So the exoplanet detection methods that we have used till now used indirect measurements. That is, it used the effect that an exoplanet causes its home star to have. So it uses that to infer or deduce the presence of an exoplanet. But how this is different is that in this we directly image the exoplanet itself. So it is much more reliable. But on the other hand, this is very difficult to do because the starlight will blind out the exoplanet itself. So like this is done in very less situations. So very large telescope can do this direct imaging of exoplanets, and it can also do radial velocity measurements, transit observation, and it can also use high resolution spectroscopy to find out the atmospheric characterization of exoplanets. So now that we know what we are searching for, which are biosignatures, now that we know how we are searching for, which is using spectrums and space curves, and we also know what we are using to search for these, which are telescopes and satellites, let us go through some case studies to apply all the techniques that we know till now to like get a solid understanding of what we learned till now. So first case study is an exoplanet called K218b. So K218b is a sub-Neptunian exoplanet, which means that it is like slightly less mass than a Neptune, and it is like 124 light years away from Earth, and it is in the habitable zone of its star, which is a red dwarf. So it has shown compelling signs for potential life forms. It was first observed by Hubble and subsequently by the James Webb Telescope, and it both of them reveal the presence of water vapor and hydrogen-rich atmosphere. These were obtained by analyzing the transmission spectroscope of its transmission spectrum of its home star. So this is also like has possibility of having methane and carbon dioxide. So all of which are key biosignatures. And very recently a breakthrough was found when a molecule called dimethyl sulfide, which is DMS, a molecule that is primarily only produced by life on Earth, was found in this planet. So we need further confirmation because scientists do argue that while DMS is produced only by life on Earth, there is a possibility that in this planet it was produced by non-life sources or abiotic sources. So we need to like research on possible abiotic causes for DMS. So this is a very very good spot for extraterrestrial life research. So what it is speculated is that K218b may possess a Iasian world environment. What does an Iasian world environment mean? It means a hydrogen-rich atmosphere over a liquid water ocean. So it is one of the most promising exoplanets for an extraterrestrial life. So the next case study we are going to see is the Europa Clipper mission. Europa is a moon of Jupiter. So it is considered to be the prime spot for finding life inside the solar system. So why so? Because we are speculating that it has beneath its icy surface there is a liquid water. So basically what happens is that Jupiter has enormous gravity and it can potentially make this Europa moon expand and contract continuously as it orbits around Jupiter. This causes heat to be produced, which is enough to keep the water liquid. And also for life to exist, there are several important chemical reactions such as which Adirat discussed before, which can only happen when the temperature is not too cold. And this is possible source for heat in Europa. Also, it is speculated that the rocky seafloor may contain hydrothermal vent activity, which is also a heat source. So this is like a prime spot to find out life inside the solar system. So Europa Clipper is a space probe that was developed by NASA to study Europa. It was launched on October 14th of 2024 and it was equipped with several advanced instruments such as radars, spectrometers, magnetometers, cameras and so on. So this spacecraft will perform nearly 50 flybys of Europa while orbiting Jupiter. So you guys would have seen several science fiction movies, and you all would have known about how we speculate that life could have existed on Mars in the past, because Mars once contained liquid water. So basically, so we are searching for life in Mars, and that's why we sent Perseverance rover. This is the successor of several rovers that we sent, like Spirit, Opportunity, and Curiosity. So Perseverance rover landed on Mars on February of 2021. It was specifically designed to search for signs of ancient microbial life in the Zero crater. So Zero crater is was believed to be a huge lake in the past. So it has lots of sediments, and hence it has lots of possibility for having possible biosignatures and presence of life. So Perseverance has sophisticated tools like Sherlock and Pixel, which are basically high resolution cameras and spectrometry instruments that is used to analyze the chemical mineral composition of Martian rock and soil. So it one of the most interesting part of Perseverance rover is that it can get the soil, it gets to collect soil, puts it in a sealed container and leaves it in specific spots in Mars. Why does it do it? Because when we send a manned mission to Mars sometime in the future, we can go collect the soil sample from Mars, bring it back to Earth, and then analyze it in a much more in-depth fashion. So this is like a very interesting and ambitious project that has been undertaken by us. So now that we know about how we are searching for life, next we will see how, if life exists, how it will be, what is intelligent life, and so on. So Haricharan will continue. Go over to Haricharan.
Thank you, Abhishek. So, a warm welcome everyone. I am Haricharan from Engineering Physics, IIT Madras. Hope I am audible. Okay. So, I would like to use this wonderful opportunity to share some content in astrobiology. So, Abhishek was talking about the ongoing missions for search of life in the solar system. Now, let us continue the discussion with some upcoming missions for the search of life within the solar system. So, first, let's see about upcoming missions to Mars. Some of the upcoming missions to Mars include the Mars Sample Return mission by NASA and the Tianwen 3 Sample Return mission by China. So, what is the aim of these missions? The aim of these missions is to collect Martian soil samples and bring them back to Earth. And then we have the ExoMars Rosalind Franklin as a collaboration between NASA and European Space Agency. So, what is the aim of ExoMars Rosalind Franklin? So, the major aim of this mission is to drill 2 meters deep into the surface of Mars to find any signature for search of life, signatures for life in the past. And then we have the Mangalyaan 2 mission, which is expected to happen around 2028. So this would be an orbiter, much like Mangalyaan 1. And then we have the Martian moon exploration mission by Japan. So the major aim of this mission is to examine the Martian moons, Phobos and Deimos, and return samples from Phobos. And now let us see some of the upcoming missions to Europa. Uh, so so NASA's Europa Clipper mission and the European Space Agency's Jupiter Icy Moons mission are some of the ongoing missions for search of life in Europa. And these missions are the Clipper is expected to reach Europa by around 2030 and 2031 respectively. So the further missions to Europa will only be planned after the observations we obtained from these missions. So the further missions will be confirmed only after 2030s, but we still have several missions proposed for Europa. So NASA has proposed a Europa lander and China has proposed an orbiter, but they are not still confirmed. So now let us move on to the next topic of the session. So before moving on to the next topic, let us start with the event. So it is the year 1947. So a businessman and pilot named Kenneth Arnold is flying near the mountain Rainier in the United States. So when he's flying in his flight, he actually sees 9 crescent-shaped objects in the sky. So the sight was both frightening as well as fascinating. So once he returned to his hometown, he reported to the media and government about what he saw in the sky, and he estimated the speed of these objects to be around 1900 kilometer per hour, which is highly unlikely for any aircraft at that time. Uh, so he talked one day. He talked about this sighting to a newspaper. So they called it an unidentified flying object or a UFO, and he told the news channel that these objects were moving in the sky like saucers would move on the surface of water. But what the newspaper did is that they misinterpreted his message as saucer-shaped objects. So that is how UFOs obtained their classical shape of a saucer. So after this incident, about from 1952 to 1969, about 12,000 UFO sightings were recorded across the globe, and all these sightings embraced the scientific community to actively start the search for intelligent life. So for rest of the session, we would be seeing about the theoretical approaches that were made for the search of intelligent life across the galaxy and universe. So now what is intelligent life? We are not actually sure of what makes life intelligent. So what we do, we consider human beings as a model organism and take the general characteristics of human beings as the characteristics of all intelligent life. So some of the characteristics of human beings include higher cognitive skills, which includes memory, reasoning, problem solving, social intelligence. What is social intelligence? So it is the knowledge of one requires to maintain a proper relation with other members of the society. And then we have a complex method of communication, which is the languages. And then we have complex social structure and collaboration. And then we have self-awareness and awareness of death. So what is self-awareness? So self-awareness is the ability to identify or know yourself, while awareness of death is the ability to understand death of other members of the group or other members of a society. And then we are human beings also have cultural behaviors and knowledge. Cultural behaviors in the sense it refers to the practices and knowledge that is passed from one generation to the next generation. So are human beings the only organism on earth who possess these characteristics? No, we have other organisms as well, but these organisms don't possess intelligent characters as complex as humans. For example, we have chimpanzees. So chimpanzees are the closest living relative to man. So they are known for their higher cognitive skills, tool use, and cultural norms. So what you are seeing in the screen is a chimpanzee which is using a stick to capture termites. So when scientists looked at the tool usage of chimpanzees, they found that the knowledge of tool usage varies between different groups of chimpanzees. And they believe that the knowledge of tool usage is actually passed down as a cultural tradition in chimpanzees. And then we have elephants and dolphins. So elephants and dolphins are known for their higher cognitive skills, and they are also capable of self-awareness, and they are also aware of death. So what you are seeing in the screen is elephant and a dolphin. They are identifying themselves by looking in a mirror. And now let us have a look at crows. Crows are one among the most intelligent birds on earth. And among crows, the most intelligent crows are New Caledonian crows. And the cognitive or the problem solving skills of a Caledonian crow is equivalent to that of a 7-year-old toddler. And then we have whales. What is so unique about whales? So whales are known for their complex method of communication, which is under research. And they are believed to have a primitive language among themselves. And what you are seeing in the screen is a whale that is breaching or jumping on the surface of water in order to reveal its location to other whales. And now we had a look at what is intelligence or what is intelligent species. Now, how do we quantize the level of advancement of a hypothetical intelligent species, or how do we classify intelligent civilization? So an approach was made by Nikolai Kardashev in the year 1964, which is the Kardashev Scale of civilization. Now, what is the basis of the classification? So what Kardashev did is that he looked at the history of human beings and found that as human beings became more and more advanced, the energy demand of human beings started to increase. What you are seeing is a graph which shows the energy consumption of human beings from 1800 to 2019, and we can see as after the industrial revolution, the energy demand of human beings started to increase exponentially. So Kardashev made an assumption that all intelligent civilization will have an ever increasing demand of energy. So he classified civilizations as type 0, type 1, type 2, and type 3, and so on based on the amount of energy they consume. Now, what are type 0 civilization? A type 0 civilization is also called as a biological civilization. They have an energy consumption in the range of about 10 power 6 watts. So this refers to a small population of beings who are in their primitive state of technological advancement. Now, what is type 1 civilization? A type 1 civilization is also called a planetary civilization. So they have an energy consumption in the range of 10 power 16 watts. So if a civilization has the ability and the need to use all energy resources available on their home planet, then they are referred as a type 1 civilization. So if we take Earth for instance, if human beings are capable of using all energy resources available on Earth, like solar power, wind power, hydro power, and the non-renewable resources like coal and petroleum to their maximum extent, then we would attain the status of a type 1 civilization. Now, what is a type 2 civilization? A type 2 civilization is also called as a stellar civilization. They have an energy consumption of about 10 power 26 watts. So these beings have used most of the energy resources on their home planet, and now they have moved to the star for energy consumption. So how do they consume the energy? They will build certain megastructures around their star, like a Dyson sphere, in order to consume the energy output of the star. More about Dyson sphere in the upcoming slides. Now, what is a type 3 civilization? A type 3 civilization is also called a galactic civilization. So this refers to the civilization which is capable of consuming the energy resources that are spread across a galaxy. So they have an energy consumption in the range of 10 power 36 watts. Now let's see about the Dyson sphere. So as I said, a Dyson sphere is an hypothetical advanced technological megastructure that which is used to consume a major part of radiation output of a star. So this is how a Dyson sphere may look like. You can consider Dyson sphere as a mega solar panel or millions of solar panels that are revolving around the star in a close proximity in order to observe the radiation output of the star. So a Dyson sphere is a characteristic feature of type 2 civilizations and higher in the Kardashev scale. A Dyson sphere is actually inspired from a fictional novel Star Maker by Olaf Stapleton in the year 1937. The first scientific approach to the Dyson sphere was made by Fermi Dyson in 1960. He studied about the possibility and feasibility of such a structure and said that alien civilization may construct a Dyson sphere in order to use the energy output of the star. So why are Dyson spheres so important? Because we can find or we can detect a Dyson sphere using highly advanced telescopes. For example, let us consider the star Tabby star, or also called as KIC 8462852. So it is a star in the Cygnus constellation about 1470 light years away from Earth. So what is so unique about the star? So the star shows an unpredictable pattern of change in brightness. So in certain intervals of time, the brightness of the star drops about 22% of its maximum magnitude. So several reasons have been proposed to explain the behavior of the star. Some say that the star has millions of comets revolving around it. Some say it is because of a dust cloud that is passing before the star, and some say it is because of a megastructure like the Dyson sphere that is being constructed across the star. So scientists are observing the star with advanced telescopes, and none of these theories have been confirmed yet. So now let us have a look at the Kardashev constant. So Kardashev constant does nothing but it signifies the position of a civilization in the Kardashev scale. So when we take human beings for instance, suppose the Kardashev constant for human civilization is about 0.7265. So we are about to reach the status of a type 1 civilization. And we have the value of the Kardashev constant purely depends on the energy output of a civilization. The Kardashev constant is 1/10 of the log to base 10th of the power consumption of a civilization over a million. So as you can see, the Kardashev constant purely depends only on the power consumption of the civilization. And with the help of this Kardashev scale, we can classify different hypothetical civilizations. And now we had a look at how to classify civilizations. Now, what is the approximate number of intelligent species that may be present in the Milky Way galaxy? So, an approach to find the number of intelligent species was made by uh, Frank Drake in 1961. So, he proposed the Drake's equation. So, what is the Drake's equation talking about? It signifies the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. In simple words, it tells about the number of alien signals we would be receiving every day. So it is a simple equation. The Drake's constant n is a product of different factors like R star, which is the rate of star formation in the Milky Way galaxy. FP is a probability that a stellar system has planets. N is the average number of planets in the habitable region. And FL is a probability that life evolves in a planet that is present in the habitable region. And FI is the probability that intelligent life evolves in a planet that has life. And FC is a probability that an intelligent life would release detectable signatures or radio waves into space. And finally, L is the duration for which a civilization would release such detectable signatures. One major drawback of the Drake's equation is that it has the presence of a lot of uncertain quantities. So, for example, when we had a look at R star, the rate of star formation, it is known with a good amount of certainty. We can measure the rate of star formation with modern technologies and metrics. But as we move to the right, when we look at the value of L, duration for which radio waves are being released, so it is highly uncertain. We can only make assumptions to find the value of L. We don't have any technology to measure the value of L. So several estimates have been proposed to the Drake's equation, and the most modern estimates are as follows. So it says the rate of star formation in the Milky Way galaxy is about 1.5 to 3 stars a year, and the probability it has planets is 1. That is, most of the stars in the Milky Way galaxy has planets around them. Average number of planets in the habitable region is 0.2. The probability that life evolves in these planets has different estimates that vary from 5 into 10 power minus 5 to 0.13. And what is the probability that intelligent life evolves in the planet that has life varies from 1 in a billion to 1. And then we have the probability that they release detectable signs into space is 0.2. And then finally, the duration for which they would release these signatures actually varies from 304 years to a billion years. So, due to various estimates, the lower value of n is modern estimate of n is about 9.1 into 10 power minus 13, while the higher estimate is about 15.6 million. So, the lower estimate states that we may be the only intelligent species who are present in the galaxy and we will not receive any alien signals. While the higher estimates say that we should be receiving thousands to millions of signals every day. But we are somehow not able to detect these signals. So several changes have been proposed to the Drake's equation over these years, and the Drake's equation has been modified several times. Now let's move on to our next topic. It is the year 1950, when a scientist named Enrico Fermi proposed a set of statements. So he says that our galaxy is about 13.6 billion years old, but the solar system is only 4.5 billion years old. And he also says that Earth is a typical planet, and there may be several planets in the Milky Way galaxy with conditions similar to that of Earth, which may have formed much before Earth. Because of that, our civilization may not be the only nor the earliest civilization of the galaxy. So there may be alien civilization which may have evolved much before human beings, and these civilization would have attained the status of a type 2 civilization by now. So interstellar travel is highly difficult for human beings, but it must not be difficult for advanced alien civilizations. So galactic colonization, if a civilization has unlocked the key to interstellar travel, then they would be able to colonize all habitable planets in the Milky Way in a few million years. So the galactic colonization would take about a few million years, which is small when compared with the age of the entire Milky Way galaxy. So though we have several UFO sightings, none of these sightings provide a valid, scientifically acceptable evidence for the visit of aliens. So if all these statements are true, then where are the aliens? Why have no aliens visited Earth? So this question troubled astronomers. So this question was finally stated as the Fermi Paradox by Carl Sagan. So various solutions have been proposed for the Fermi Paradox, and let's see some of the most accepted and renowned solutions for the Fermi Paradox, or why aliens have not visited Earth. So before moving on to the first hypothesis, I would like to discuss an event. So one principle that is followed by most of the wildlife photographers is that they don't want to interfere in the natural way of life of wildlife animals. And but this is not the case always. So in November 2018, a crew of wildlife cameramen were filming emperor penguins in Antarctica. So they discovered a group of penguins which has been isolated from the rest of the community, and it has been stuck in a ditch or a hole that is present in the region. They have been stuck there for almost 2 days following a terrible storm. So they found that some of the chicks had perished in the ditch without food and exposure to extreme weather conditions. And they also realized that without helping, all these penguins would die. So what the crew members decided is that they decided to act beyond the protocol and save all the lives of these aliens. So what you are seeing is an image of the wildlife photographers who are digging a shallow ramp near the hole or the ditch by which through which these emperor penguins would escape and join with the rest of the community. Why did I want to discuss this event here? Because I wanted to signify the ethical concerns of humans to not interfere in animal life. So let us move on to the first solution to the Fermi paradox, the zoo hypothesis proposed by John Ball in 1973. So according to this hypothesis, extraterrestrial beings are highly advanced and they have reached the status of a type 3 civilization already. And these extraterrestrial beings are seeing human beings as primitive organisms. So they don't want to interfere in the development of human beings, as human beings, similar to human beings, don't want to not wanting to interfere in the life of animals. So they are using their advanced technology to hide themselves from the vision of human beings. So in a nutshell, alien civilizations are like eternals from Mars. So they have been here all these years, but they have not yet interfered. So it is one of the earliest solutions that was proposed to the Fermi paradox. Now let us move on to the next solution that was proposed to the Fermi paradox, which is the rare Earth hypothesis, which was proposed by Peter Ward and Donald Brownlee in 2000. So according to this hypothesis, Earth is not a typical planet. Earth is extremely special. It is a rare combination of all features that are required for life to evolve. So this hypothesis says that apart from having a liquid medium, a planet also needs to have other characteristics as well. So this hypothesis states the significance of plate tectonics, active cores, and tides, and etc. So why are plate tectonics important in the origin of life? So plate tectonics play an important role in the cycle of minerals in the crust, and it also plays an important role in the formation of hydrothermal vents. What is so special about hydrothermal vents? Hydrothermal vents is a region where we can find an ecosystem that is completely independent, that works completely independent of sunlight. So some researchers say that hydrothermal vents played an important role in the evolution of a life or the origin of life. And then we have an active core which gives a strong magnetic field that protects us from the harmful rays of sun. And the tides, the regions affected by tides act as an ecotone between aquatic ecosystems and terrestrial ecosystems and play an important role in the evolution of aquatic life into terrestrial life. So, according to this hypothesis, human intelligent life is only present in Earth because Earth is extremely special and rare. And now, let us move on to our next hypothesis. Before moving on to our next hypothesis, let us have a look at a video clip. So, what you are seeing is a group of toddlers who are trying to climb a staircase. So, according to the next hypothesis, the life in different biospheres in different planets has to cross different barriers to give rise to complex or intelligent life forms. So, the course of evolution of these life in different biospheres is much similar to how these toddlers are climbing these staircase. It is not easy for all the life, all toddlers. We are let's move on to our next hypothesis, which is the great filter hypothesis proposed by Robin Hansen. So, what is the hypothesis telling? So, this hypothesis states the presence of several barriers in the course of evolution of life into complex and intelligent life form. What is a barrier? A barrier could be considered as an existential threat that is being faced by the living organisms, or it is an extremely rare probability event that has to occur in the evolution of life from primitive to highly advanced living organism. So we could consider a barrier as a step in a staircase. There have been several barriers that human beings or the life on Earth has crossed over the years. So, according to this hypothesis, aliens have not visited Earth because humanity is the first intelligent life forms that has evolved. Humanity is too lucky to have crossed these barriers over the years. Or this hypothesis also states that there are several intelligent organisms like human beings in the galaxy, but similar to human beings, these organisms are facing several barriers or existential threats as they are becoming more and more advanced. Now let us have a look at some of the barriers. So one such barrier that life on Earth has managed to cross is the endosymbiosis. So Adrija clearly explained what is endosymbiosis. So according to endosymbiosis theory, mitochondria and chloroplasts that are found in the eukaryotic cells were actually free-living prokaryotic bacteria, which was engulfed by another unicellular organism. So this is expected to occur about 1.8 billion years ago. So why is endosymbiosis a barrier in the evolution of life? Because some researchers suggest that endosymbiotic events are extremely rare events. So they say that endosymbiosis event could have not occurred in all the planets which has unicellular organisms. Only the life on Earth has managed to accomplish endosymbiosis in a given amount of time. And now let us have a look at some of the barriers which we are already facing right now, or the barriers which lie ahead. So one such barrier includes the climate change. Why is climate change a barrier? So as any alien civilization consumes most of the energy resources that are available on the planet, they would absolutely change the conditions of the biosphere, or they would change the atmospheric conditions of their planet. So when we take human beings, for instance, we are using fossil fuels for our energy needs, and we release a lot of greenhouse emissions which increases the global temperature, leading to climate change. So we are already facing a lot of issues due to climate change, which is hindering the advancement of human beings. So this may be common for all alien civilization. And next, another barrier which we are facing are the technologies that get out of hand. So when we had a look at human beings, they are well known for using advanced technology without fully understanding them. For example, around the time of First World War, uh, soldiers used to have radium in their watches in order to see time even in a reduced amount of sunlight. But the problem is that the presence of radioactive materials in your outfits will certainly have harmful effects on your body. Similarly, we were using chlorofluorocarbons in our refrigerators, and this led to the depletion of ozone in our atmosphere. So similarly, there may be an alien civilization which may have made a super advanced AI, and the AI may have led to their own extinction. So technologies are also a barrier that we have to face. And another barrier which we are facing is global conflicts. So as any civilization starts to use most of the energy resources that are available on their planet, this will ultimately lead to internal conflicts or competition for resources. So if we had a look at the last century, there have been several incidents where human beings almost went to the brink of extinction by a full-blown nuclear war. So there may be alien civilization who went extinct due to internal conflicts. And then we also have several pandemics. um, as the density of population increases and as the transportation facility develops, the possibility of a pandemic only increases. So, similar to these challenges, there may be several other challenges that we human beings and other alien species also have to face along the course of evolution, which would slow down their rate of advancement, preventing them from exploring the space or coming to Earth. Now, let us move on to our next hypothesis. So, before moving on to the next hypothesis, let us start with the story. So let us consider a hunter in a dark forest. So this hunter used to roam across this dark forest to collect food and supplies. He has spent most of his lifetime in this dark forest for a very long time. He doesn't have a name, for nobody calls him. Let us call him Bob, for instance. So Bob is very lonely and he's roaming across the dark forest in search of resources. One day, Bob spots another hunter in quite a far distance. What will Bob do? Go and talk to the other hunter and end his loneliness? But what if the other hunter kills Bob and takes his food supplies and other resources that Bob has? So, should Bob just leave the area without any notice? But what if the other hunter spots Bob in a after some time and kills him and takes all his resources? So, though Bob is extremely lonely, Bob is selfish. So, his own survival is the only thing that matters to him. So, Bob aims and just kills the other hunter without warning. So, this is what Bob does, and this is what all hunters would do in the dark forest when they spot another hunter. So, let us move on to our next hypothesis, the dark forest hypothesis. So this hypothesis was proposed by Liu Cixin in his novel The Dark Forest in 2008. So right now it is one of the most plausible and again one of the most controversial hypothesis to the Fermi paradox. So this hypothesis says that alien civilization behave like hunters in a dark forest. Why do they behave like hunters in a dark forest? Because all intelligent civilization are expansionist and they have an ever increasing need for energy resources. So, an alien civilization would only see another alien civilization as a threat and they would not trust each other and they will tend to destroy other civilization at sight. So, when a civilization spots another civilization, they will try to develop certain advanced interstellar weapons to destroy the other civilization. So this hypothesis actually derives its concepts from cosmic sociology and game theory concepts. So according to this hypothesis, there are only two types of civilization in the entire universe. One is the type of civilization which are hiding and they have not exposed themselves to other civilization, and the other civilization type of civilization are those who have exposed themselves and went extinct. So, according to the dark forest hypothesis, aliens will not visit Earth because they don't want to expose themselves, and the other important uh, point that is given by dark forest hypothesis is that human beings have not yet been destroyed by alien civilizations because we have not yet reached the amount of technological advancement to expose ourselves to other civilizations that may exist. So apart from these hypotheses discussed, there are several other hypotheses as well, and some hypothesis which states that we are in a simulation. So it is a simulation hypothesis. So this was proposed around 2003. So according to this hypothesis, we are in a simulation which of we are in a simulation world, and we are the only civilization who are being simulated. And we have another hypothesis which states that aliens do not expand into space. They would only use the energy resources that are available on their planet, and they would not venture out into space. And then we have another hypothesis which states that alien civilizations are actively communicating with each other, but human beings have not yet decoded the method of communicating with advanced alien civilization. Okay, so finally, we have almost reached the end of the session. So, everyone, please be free to ask your doubts. So, you can ask your doubts from the content I have covered, or you can also ask your doubt from the content covered by Adrija and Abhishek. So, you can post your doubts in the chat. Please be free to ask your doubts. Any doubts, yes? Can you also use a Google form that was posted in the WhatsApp channel to post your queries or doubts if you have? So we will be providing an assignment which is related to the topics that has been covered in the session. So, and we would also share the resources which we have used for the session in the WhatsApp channel. So is there anything else? And our next summer school session will be on 13th July. So please join the next summer session also, guys. It will also be interesting. And thank you for your participation. I hope we had you engaged. Okay. So with this, we are Horizon and Biotech Club signing off. Thank you. Thank you.